Welcome, future construction moguls. Today we're talking about the Goethals Bridge Replacement Program, or as I like to call it, how to replace a 1928 relic without breaking the bank, or New Jersey. This $1.5 billion project is basically the construction industry's version of a masterclass. It's got everything: public-private partnerships, innovative financing, and, spoiler alert, 3D printing. Yes, we're printing bridge parts now. The future is weird and wonderful. So, buckle up, because we're about to dive into how the Port Authority of New York and New Jersey managed to pull off what many thought impossible: delivering a major infrastructure project ahead of schedule. I know. Pinch yourself, it's real. All right, let's talk about this bridge's glow-up. The original Goethals was built in 1928, back when people thought 4 narrow lanes with no shoulders was perfectly fine. Spoiler, it wasn't fine. It was a traffic nightmare serving 132.7 million passengers annually. That's like the entire population of Russia crossing your bridge every year. Yikes. So what did they do? They said, out with the old, in with the P3. That's public-private partnership for those keeping score at home. They used something called a DBFM structure: design, build, finance, maintain. Basically, the private sector does the heavy lifting while the public sector keeps control. It's like hiring a really good contractor, but you still own the house. Here's where it gets spicy. This project finished 5 years ahead of traditional procurement methods. 5 years! That's like finishing a 4-year degree in 18 months. The secret sauce? A 40-year contract with $56.5 million in annual availability payments. Think of it as a construction subscription service, Netflix, but for bridges. Bottom line, $1.5 billion done faster, and it works. The Northeast's first surface P3 was basically construction's way of saying, yeah, we can do this too. Every great project starts with a problem. Actually, in this case, it started with multiple problems having a party, and everyone was invited. The physical problem. Picture this: it's 1928, you're designing a bridge, and you think, you know what drivers will love? 10-foot lanes with absolutely no shoulders. Fast forward to modern times, and you've got a bridge that's functionally obsolete. We're talking structurally outdated, geometrically challenged, and serving as a critical choke point for 132.7 million people. Oh, and $872 million in regional economic activity was at risk. No pressure. The financial roadblock. Meanwhile, the Port Authority of New York and New Jersey, let's call them PANYNJ because that's easier, was facing a severe cash flow crunch. They had an aggressive capital program, but limited liquidity. They couldn't just issue a $1.5 billion municipal bond because they lacked the public debt capacity. It's like when your credit card is maxed out, but your roof is leaking. You need a solution, and it can't involve going further into debt. The solution? Pivot from traditional public funding to a P3 DBFM model. They basically said, private sector, you design it, build it, finance it, and maintain it for 35 years. We'll pay you annual fees, but you take the risk. And, spoiler alert, it worked. This is construction management gold, people. All right, time to put on your finance hats. Don't worry, they're surprisingly comfortable. This slide is basically the organizational chart of who does what and who gets paid. At the top, we have the public owner, PANYNJ. They retain asset ownership, set toll rates, and collect 100% of toll revenue. They're the landlord who still owns the building. Below them is the private partner, NYNJ Link Partnership, a special purpose vehicle, SPV, that's 90% Macquarie and 10% Kiewit. Think of an SPV like a pop-up company created just for this project. It exists, does its job, then disappears into the sunset. The PANYNJ pays the private partner availability payments of $56.5 million per year. In return, the private partner delivers the asset and performance. They handle design and build, Kiewit Weeks Massman joint venture. Finance, equity plus debt. We'll get to that. Maintain, NYNJ Link for 35 years. Here's the kicker. There's a quote at the bottom worth tattooing on your brain. P3s are not privatization. They are long-term performance contracts where the public agency retains control. Translation: the public still owns the bridge. The private sector just runs it like a well-oiled machine. This is partnership, not a sell-off. Important distinction. Now we're getting into the money. Everyone's favorite part. Let's talk about how you finance a $1.5 billion bridge without selling your soul. Imagine you're stacking Legos, but each Lego is a different type of money. At the bottom, we have TIFIA Direct Loan, $473.7 million, federal credit. This is like getting a super low-interest loan from Uncle Sam. TIFIA stands for Transportation Infrastructure Finance and Innovation Act, which is government speak for, "We'll help you pay for this." Next up, Private Activity Bonds, PABs, $453.3 million, tax-exempt. These are bonds issued by the private partner, but they're tax-exempt, which makes them cheaper. It's like a discount coupon for borrowing money. Then, private equity, $106.8 million, NYNJ Link. This is the private partner's skin in the game. They're investing their own money, which means they're really motivated to make this work. Finally, at the top, public contribution, $125 million, milestone payments. The Port Authority chips in some cash as construction hits milestones. Think of it as paying your contractor as they complete each phase. The strategy. This project uses approximately 85% debt. Why? Because it lowers the cost of capital compared to pure private equity, and it avoids caps on public municipal bonds. Translation: borrowing smartly is cheaper than paying cash, and they structured it to maximize efficiency. This is financial engineering at its finest, folks. Let's talk about the secret sauce that makes P3s work. Performance-based economics. This is where we separate the amateurs from the pros. See that giant check mark and dollar sign? That's the key. The private partner gets paid a flat fee of $56.5 million per year. But, and this is a big but, payment is made only if the bridge is open and performing to specification, irrespective of traffic demand. Let's break down the risk transfer. Demand revenue risk, retained by PANYNJ, public. If traffic drops and toll revenue plummets, the private partner still gets paid. PANYNJ absorbs that risk. This is crucial because it made the project attractive to investors. Performance O&M risk, transferred to NYNJ Link, private. If the bridge closes for repairs, payment gets docked. This incentivizes the private partner to keep everything running smoothly. No one wants to lose money because a cable snapped. Here's a fun analogy. Imagine you hire a lawn service with a subscription fee. You pay them monthly, but if they don't mow your lawn, you don't pay. Same principle here, except instead of grass, it's a bridge carrying millions of people. This model aligns incentives perfectly. The public protects against revenue risk, which they can't control, and the private sector takes operational risk, which they can control. It's elegant. It's smart. It's construction management poetry. Welcome to the risk allocation matrix, or as I like to call it, who's on the hook when things go wrong. This is one of the most important slides in P3 project management. Notice a pattern? Under traditional procurement, the public sector eats almost all the risk. Design goes over budget? Public problem. Construction delayed? Public problem. Bridge needs maintenance in year 20? Public problem. Under the DBFM model, most of that risk gets transferred to the private partner. They're on the hook for design, construction, delays, and maintenance. This creates a powerful incentive for them to get it right the first time. But, and here's the nuance, the public retains demand revenue risk. Why? Because the public controls toll policy and traffic patterns are unpredictable. It wouldn't be fair, or smart, to make the private partner gamble on things they can't control. Environmental approvals are shared risk because, let's be honest, dealing with regulators is everyone's problem. This matrix is the backbone of P3 success. Allocate risk to whoever can best manage it. Simple in theory, brilliant in execution. Now let's talk about constraints, because nothing says fun engineering challenge like the Federal Aviation Administration breathing down your neck. The constraint. Newark Liberty International Airport is right next door, and the FAA imposed a strict height restriction. The towers could not exceed a 900-foot span. For context, that's unusually short for this type of cable-stayed bridge. It's like being told to build a mansion, but you can only make it 1 story tall. The solution. Outward-leaning V-towers. Look at that photo. Those towers lean out, not straight up. Why? Unusually squat towers for this span length. They had to stay low, so they went wide. Outward lean improves aerodynamic performance. Wind hits the bridge differently, reducing stress and vibration. Safety upgrade. The angled design prevents ice from falling onto the roadway below. No one wants a frozen projectile hitting their windshield at 60 miles per hour. This is a perfect example of performance-based design. The Port Authority didn't say, build towers exactly like this. They said, keep it under 900 feet and make it safe. The design team responded with innovation. And honestly, those V-towers look cool. Form meets function, people. This is how you turn a constraint into a signature feature. All right, this is where things get really cool. Let's talk about the impossible anchor boxes. The challenge. The bridge uses stay cable anchorages that had to fit inside short, squat towers. Steel fabricators took one look at the design and said, nope, impossible to fabricate. They literally refused to bid on it. The breakthrough. Enter Parsons, the engineering firm. They said, "Hold my protractor," and printed a 3D model to prove the fabrication sequence was viable. Let me repeat that. They used 3D printing to solve a construction problem. We're living in the future, folks. Once the steel fabricators saw the 3D model, they realized it was possible. The design features: fully embedded in concrete. These boxes are buried in the tower structure for stability. Internal access for 100% inspection. Engineers can physically walk inside to check everything. Extended to full width of towers for maximum efficiency. No wasted space. This is innovation born out of necessity. When people say something can't be done, sometimes you just need to print it and prove them wrong. Lesson: performance-based specifications encourage creative solutions. If the Port Authority had been prescriptive, use this exact method, we might never have gotten this innovation. Let's talk about future-proofing, because this bridge isn't just built for today, it's built for your grandkids' grandkids. Check out these features. Weigh in motion, WIM. Sensors track heavy truckloads in real time. Why? So the bridge can monitor stress and wear. It's like a Fitbit for infrastructure. Structural health monitoring, SHM. Embedded sensors detect stress and vibration. If something's wrong, the bridge knows before it becomes a problem. Preventive maintenance, baby. Weather stations. Variable message signs update based on current conditions. Fog rolling in? The signs warn drivers. Ice forming? They adjust speed limits. It's smart infrastructure. This is the 21st century approach to asset management. Instead of waiting for something to break, you monitor constantly and fix proactively. It saves money, extends lifespan, and keeps people safe. Plus, it looks awesome at night with those LED lights. I'm not saying aesthetics matter, but okay, I am saying aesthetics matter. If you're spending $1.5 billion, it better look good. Let's compare the old bridge to the new one, because this is basically a before and after makeover show. 1928 bridge. 4 10-foot lanes. Imagine driving a truck through a hallway. No shoulders, breakdowns, instant traffic nightmare. Steep grades. Your car's transmission hated this bridge. No pedestrian access. Cyclists and walkers? Forget about it. Replacement. 6 12-foot lanes. Actual room to breathe. Full inner and outer shoulders. Breakdowns don't shut down the entire bridge. 10-foot dedicated pedestrian bike path. You can walk across now. Future-proof. Capacity for mass transit corridor between spans. Planning ahead for rail? Brilliant. That last point is key. The new bridge has space reserved for a potential transit line. They didn't build it yet, but they left room. That's forward-thinking design. Translation. The old bridge was a cramped, dangerous relic. The new bridge is spacious, safe, and ready for whatever the future throws at it. User experience matters, and this project delivered. Construction projects get a bad rap for being disruptive, but the Goethals team actually gave a damn about the community and environment. Let's break it down. Ecosystem sensitivity. Construction schedules were adjusted to accommodate flounder mating seasons in the Arthur Kill Strait. Yes, you read that right. They worked around fish sex schedules. Because when you're building in a waterway, you respect the ecosystem. wholesome infrastructure, folks. Community integration, noise mitigation for local schools. No one wants construction crews drowning out algebra class. Historical preservation via PBS documentary and history books. They documented the old bridge before tearing it down. It's infrastructure with a story. Aesthetics, programmable LED lighting and clean lines design to reduce visual clutter. This bridge doesn't just work, it looks good doing it. Look at that photo. Those lights aren't just functional, they're art. The bridge has become a regional landmark. Lesson for public agencies. Good projects don't just solve technical problems. They respect communities, protect environments, and add value beyond transportation. This is how you build public trust. Let's zoom out and talk policy, because this project was ahead of its time. The GBRP model anticipated the goals of the Infrastructure Investment and Jobs Act, IIJA, before it even existed. Here's how. Private Activity Bond, PAB, expansion. The cap doubled from $15 billion to $30 billion. This project helped prove that PABs work for major infrastructure. TIFIA growth. Expanded eligibility for transit-oriented development and airport projects. The Goethals project used TIFIA effectively, showing it's a viable tool. Asset recycling and value for money, VFM. New requirements for VFM analysis on projects over $750 million. The GBRP set the standard for this type of evaluation. The trend. The U.S. is shifting from pure municipal bond financing toward hybrid P3 models to close the infrastructure gap. Why? Because municipal bonds alone can't keep up with the backlog. This project was a proof of concept. It showed policymakers, hey, this P3 thing actually works. And now, with the IIJA, we're seeing these models expand nationwide. Lesson. Innovation in one project can influence national policy. The Goethals Bridge wasn't just a bridge, it was a blueprint. All right, let's distill this whole case study into 3 actionable lessons. If you're a public agency looking to do a P3, tattoo these on your brain. 1. Early private involvement. The Request for Information, RFI, process was issued 4 years before construction. Why does this matter? Because it gave the private sector time to shape the DBFM model and validate market interest. You can't just drop a $1.5 billion project on the market and expect bidders to magically appear. You need to court them, get feedback, and refine your approach. Think of it like dating. You don't propose on the first date. You date for a while, figure out if you're compatible, then propose. 2. Performance over prescription. Innovation thrives when agencies define outcomes, for example, visual quality, traffic flow, rather than prescribing exact methods. Case in point, the 3D printed anchor boxes. If the Port Authority had said, you must fabricate anchor boxes using method X, we'd never have gotten that innovation. Instead, they said, make it work, make it safe, make it last. And the private sector delivered. 03. The best value selection. Move beyond lowest bid. Score proposals on technical merit. Is this design actually good? Schedule acceleration. Can you finish faster? Long-term viability. Will this last 100 years or 20? Choosing the cheapest option often backfires. You want the best option, not the cheapest. Quality costs money, but poor quality costs more. These 3 lessons are the foundation of successful P3 delivery. Memorize them, live them, build with them. And here we are, the big finish. Let's bring it home. The Goethals Bridge replacement proves that P3s can deliver iconic, complex infrastructure ahead of schedule while solving acute public funding gaps. It stands not just as a crossing between states, but as a bridge to the next generation of project delivery. Read that again. This isn't just about a bridge. It's about a model, a way of delivering infrastructure that works. What did we learn? P3s can work in the U.S., even for surface transportation. Risk allocation matters. Put risk where it can best be managed. Performance-based design unlocks innovation. Early engagement with the private sector pays dividends. Financing matters as much as engineering. This project was completed ahead of schedule under a DBFM structure, with private financing doing the heavy lifting while the public retained control. It's proof that you can have your cake and eat it too. So the next time someone says, public-private partnerships don't work, show them the Goethals Bridge. Show them this case study. And then drop the mic.